Now another type of vertical circle is a bucket of water which is whirled in a vertical circle. If you have ever seen a demonstration of this experiment before, you will see that if you turn the bucket fast enough, then the water will remain in the bucket and will not spill. So the question is, what are the forces acting on the water such that that the water won't fall? So let's talk about again the resolution of forces at the top of the circle and also the bottom. So why do we usually resolve at the top and the bottom of the circles? Because these two positions represent the extreme positions, and all other positions in between will just have values in between these two extremes. So let's look at the top here. So what are the forces acting on the water? Be careful, we are looking actually at the water. Obviously you have the weight, but now we are our reaction force instead of your tension, because the water here doesn't feel the tension of the string, but what it feels is the normal reaction force exerted by the base of the bucket acting downwards. So why is your normal reaction force acting downwards? Most students ask me. Because normal reaction force comes from Newton's third law, meaning to say when we exert a force on a surface, then the surface will react by pushing us back. So therefore, if the water is sticking to the base of the bucket here, that means it's exerting a force upwards on the bucket, the base of the bucket. So therefore the base of the bucket will exert back a force in the opposite direction, which is your normal reaction force. So these two forces will give you a resultant force, and since it causes a circular motion, so these two force becomes my centripetal force. And rearranging, I will get the equation for my normal reaction force. Now at the bottom of the circle, you have again two forces. One is your weight, which is downwards all the time. Another one is your normal reaction force, which is upwards. So why is the normal reaction force upwards? It's because now the water is pushing down on the bucket, so therefore the bucket will push back up, so that becomes your normal reaction force. Now in order to get a resultant force upwards, which is your centripetal force, your R will definitely be bigger than your mg. So you take R minus mg becomes your centripetal force. Rearranging, and then you get the equation for the reaction force at the bottom. By comparing these two equations, we can see that the normal reaction force at the top is the smallest, and the normal reaction force at the bottom will always be the largest. So if we were to spin this bucket slower, and if it's too slow, if your V is too small, then your mv squared over R minus mg becomes 0, and then when the reaction force is 0, means the water will start to fall, because when the bucket stops pushing the water, is because the water stops pushing on the base of the bucket. It means it is falling down. So therefore, what is the speed at which the water will fall? That means what is the minimum speed that you need to give the water at the top of the circle. So once again, we assume the reaction force is 0 when the water falls. So substituting 0 into this equation, we will be able to get V equals to square root GR, which is similar to the minimum speed for the previous part, where this is the minimum speed in order for the string not to slack. And at the bottom of the circle, what is the speed that you need to give the water? So once again, we can use conservation of energy again. So the loss in KE, which is KE here minus KE here, equals to mgh, which is 2R. And after solving the same thing, same way as we did for the previous example, where we substitute the speed at the top as square root GR, cancel the M, bring everything over, and we will be able to get the same equation, which is V at the bottom is square root 5GR. So which means to say this square root 5GR is actually the same speed that we did earlier on, which is the minimum speed that we needed to give the stone at the bottom in order for the stone to go to the top and have a speed of square root GR. So which means to say if the speed here is less than square root 5GR, if you give the water this speed less than this, when it reaches here, not only will the water spill, but the string will also slack. So this is how you solve questions on vertical circle.